All right, good morning, everyone. So we're going to start a new unit today on random forests and other ensemble methods. So let me just start with some intuitions of the main theme here. So let's say that we have a biased coin, so a coin that flips on heads more than tails, and you don't know that ratio of how often it hits heads versus tails, and you want to find out. So one thing you can do is you can flip that coin. And if you flip it just once and you say, okay, whatever side comes up more often is the heavier side, then you'll be correct 70% of the time. So let's say, our coin has a 70% chance of coming up with heads, 30% tails. So if you flip it once and you guess heads, you'll be right 70% of the time. But what if we do this flipping n times, and then we choose the majority vote? So if I flip it 3 times and it comes up twice heads and once tails, then I guess heads. So it turns out if you do this, it gets better and better the more times you flip that coin. So when we do this 11 times, we get 92%. If we do this 21 times, we get 97%. 31 times, we get 99%. You can calculate these numbers if you look at the CDF of the binomial distribution. That's where they come from. But basically, the more times that we observe this random variable, the more we can learn about its statistics, basically. So with this in mind, let's relate this to classification, which is something we do. So we have, let's say, 31 different binary classifiers. Each of these classifiers is not so good. It's only correct 70% of the time. But let's say that I do this approach here, where I use all 31 classifiers and then I just look at the majority of the vote. If more than half say that the class is 1, then overall I guess that the class is 1. So if based on this experiment here, if we do this, even though the classifiers individually are correct only 75% or 70% of the time, this majority vote will be correct 99% of the time. Okay, now there is one really important thing in making that leap. When we flipped the coin, every time we flip it is an independent realization of this random variable. So down here, what we said about the classifiers is going to be true if each of those classifiers are giving us a statistically independent outcome. In other words, like if I have one bad classifier that's wrong, they're correct 70% of the time, and I just ask that classifier 31 times, nothing changes. It's still wrong 70% of the time, or correct 70% of the time. But if I have 31 independent classifiers and I do this majority vote, then I can improve my classification error rate quite a bit. So this is the idea behind these ensemble methods. So we call these sort of simple, not so good classifiers, or they could be regressors. We call these the weak learners. And then when you put them together and accumulate their outputs, we call that a strong learner. And you can see this play out in many other things in the world. So something called the wisdom of the crowd is that, when you have a crowd of people, maybe the individuals in the crowd are not so smart, but if you put everyone together, you can get something smarter. So they've done these experiments where they have like this big jar of marbles, and they ask everyone in the crowd, how many marbles is in the jar? And then, everyone gives their guess, and the guesses individually are pretty far off, but when you average all those guesses, it's actually quite accurate. So that's just another example of this. So that's essentially what this unit is about. It's about how you can take classifiers or regressors that are relatively weak on their own, but you can make a number of, train a number of them, put them together to get a much stronger classifier. And the key, as we see down here, is that you have to somehow make those different predictors act differently from one another. You have to make them act independently for this to work. And so there's many different ways of doing that, and that's what we'll talk about first. Okay. But actually, before we get into that, there's a couple details on how we do this combination. So here we talked about voting. So there's a couple different ways we can do this voting. So imagine that I have a set of base classifiers, and the main word for these sets of classifiers they use in machine learning are ensembles. So they call these ensemble methods. Okay, so what we talked about on the previous page says, let's take the majority vote of hard decisions. So by hard decisions, we mean, like in the binary case, zeros or ones. That would be the hard voting classifier that we discussed on the previous page. But there's actually something a little bit better than you can do. If these classifiers give you soft outputs, so for example, in the binary case, they would give you a number between 0 and 1, which is their confidence. If you average those confidence values together, that gives you the soft voting classifier, and that usually works a bit better than a hard voting classifier. Okay, and if you have more than one, more than binary classification, you have k different possibilities. You can think about this in terms of the PMFs generated by each one of the classifiers, and you can average those PMFs and finally look for the peak of that average PMF to give you the final prediction. Okay, so those are a couple things, hard and soft voting classifiers. And in sklearn, these are both implemented in this voting classifier. Okay, so again, what we need is diversity. We need the classifiers to be different. So you can prove that the voting classifier will be better than any base classifier if these base classifiers are sufficiently diverse. In other words, sufficiently independent. So how do we do this? Basically, we can categorize this in two different ways. Maybe we use the same model or predictor for our classifiers, but we give those classifiers different data sets. So maybe let's say I use logistic regression always, but for logistic regression, I carve up my data in different ways, train different logistic regression classifiers, and then finally combine them using these methods. Okay, so that's one approach, using different data sets. Another approach is that you actually use different prediction models. It may be the same data set. So for example, maybe I trained logistic regression, I trained SVC, I trained a neural network, and then I could ensemble or average the outputs of these three models. And the hope would be that they act a bit different. You don't expect them to be maybe completely independent, but maybe there's enough independence there such that when you average them, you actually get an improvement over each of the individual classifiers. And another question is, okay, well, what if this is not the only way to do it, different model types. You could actually, let's say I use logistic regression in all cases, but what I do beyond that is every time I use logistic regression, I use only a random subset of my total features. So the first logistic model has some subset, second has another subset of features, third has another subset of features. And by giving them different subsets of features, those logistic regression models will all be a little different. And maybe that diversity among them will be enough that I can outperform any of the individual ones. So these are the sort of things that we'll be talking about. We'll be going into a bit more detail about exactly how you do this. And everything we're saying here also works for regressors too. It's not only specific to classification. Any questions so far? Okay, so let's think about this. This first option. What are different ways of making different data sets? So there's basically two main ways to do this. Two main ways to introduce this data diversity. And the first one is called pasting, the second one's called bagging. Okay, so in pasting, this is maybe the way you'd think about doing it, is you draw training samples without replacement. So what we mean by that is, let's say I have 100 training samples, I have 10 classifiers, and I have to somehow give those classifiers different data. So I draw 10 samples for the first classifier, and now I have 90 samples left. Now I draw 10 of those for the second classifier, now I have 80 left, and so on. So at the end of the day, every sample in my original data set is used exactly once by one of those classifiers or regressors. Okay, so I'm just splitting my data to them. So this is drawing samples without replacement, because every time I draw a sample, I give it to a classifier. I do not replace it in my original data set. But the second idea is the same thing, but drawing samples with replacement. So here, I start with 100 samples, and I draw 10 randomly, give them to that first classifier, and now I still have the original 100 samples. I draw 10 randomly again, give it to the second classifier. So maybe some of the samples I gave to the second classifier I previously gave to the first, maybe not. And I do this over and over, and at the end of the day, maybe some of the samples in my original 100 I never gave to any classifier. Okay. So these are the two approaches. Pasting, which is drawing samples without replacement, or bootstrap aggregating, or otherwise known as bagging, drawing samples with replacement. Okay, so typically bagging works better than pasting. It's a more common option. So let's think a little bit more detail about this bagging idea. Okay, so usually what we do, instead of this description I gave where I had 100 samples and I drew 10 for the first classifier, usually what we do is, if I have 100 samples, I actually draw 100 for each of my classifiers. So in general, if I have n samples in my data set, I draw n for that first classifier. So that means that this first classifier may actually be given certain samples more than once. And other samples in my data set, I will never give to that classifier. In fact, you can prove that when n is large, about 1 over e, or 30% of your samples, are never given to each classifier. And so that means that 30% of the samples you're giving are actually redundant. That's just how it turns out. And that's okay. And in fact, what you can do is, for that first classifier, those 37% of samples that were not used for training, you can actually use for validation. So this is a common thing. They're called out-of-bag samples. You can use them for cross-validation. So all these different classifiers will have different subsets of your training. They'll have different validation sets. They get trained individually. They get validated individually. And then finally, you average all their outputs at the end of the day. So this is implemented in sklearn bagging classifier and sklearn bagging regressor. And you can choose which of these two strategies. You can choose bootstrap equals true for bagging, or bootstrap equals false for pasting. And you can choose this OOB score equals true if you want to do this out-of-bag cross-validation. Okay. And so this is a generic. You can give it any kind of predictor you want. sklearn predictor, it will do this stuff. Okay, any questions? All right. So this is, again, data diversity. So now we also talked about this other way of getting diversity in terms of models by using different subsets of features. So let's talk about that. So using random subsets of features is another way to add diversity. This is especially useful when you have many features, so high dimensional data, and when you have redundancy among your features. Because if there's like, one super important feature and you don't give it to a classifier, that classifier is not going to do very well. But in practical data sets, the information about the targets are usually split over a number of features. They're all a bit useful, some more than others, but that allows you to kind of split those features among your different predictors, and this works well. So now again, there's different ways to split features between predictors. You could do this sampling with replacement. So if I have 100 features and 10 classifiers, that would mean every classifier gets 10 features, and the next classifier gets 10 different features, and so on. So that's one way of doing it. Or you can do bootstrapping. So maybe what you do there, you have 100 features, 10 classifiers. You draw 100 features with replacement, give it to the first classifier. So as we know, 37% of those will be redundant. 37% of the original features will not get to that first classifier. And then you do this again for the second classifier. Now he gets 100 features, but 37% will be redundant and 37% will be missing from your total features, and so on. So we can bootstrap in the feature domain too. And in fact, we can combine this random feature stuff with the random sample stuff and do both together. So when you use both random data samples I and random features J, that's called random patches. And when you use random features but the full data, that's known as random subspaces. Okay, so these things are also implemented in the bagging classifier and regressor. If you want to use feature randomization, you just set max features less than D. And if you want to bootstrap your features, then you just set bootstrap features equals true. So they give you a lot of freedom in how you want to do things. Okay. So that's sort of an overview of how you can combine different generic predictors together, make them diverse by doing things like giving them different data, giving them different features, and then combine them using sort of a simple averaging of their outputs, either voting in classification, otherwise averaging. So the next thing to do is we'll kind of switch gears, and we're going to look at a particular style of predictor that we haven't talked about yet, but which is important, which are decision trees. And then we'll put these concepts together, and we'll get finally random forests. Before we go on, are there any questions about this generic ensembling stuff we talked about? Okay, pretty clear how we do that? All right. Okay, so decision trees are just a completely different way of doing prediction and classification than we've talked about so far. It's actually a very nice way of doing it, but it's just completely different. So this is essentially how you do it. So as always, the setup is we have some data, so we have some features. Features are, as always, d-dimensional. We'll assume that they're all, just for now, you can just assume they're all numbers, no categories, although we can actually handle categories. Actually, yeah, let's see, how do we want to do this? We will be talking about the case where some of these features are categorical, but let's just assume that there's D of them. And then we have our targets, Y, and Y could be a real number, or actually we could, they could be discrete to handle classification. So it's actually very, very generic, what we're going to talk about. Okay, so the overall approach, you can think about it in two steps. We need to partition our feature domain into L regions. So this picture here would show if I have two features, X1 and x2. These are both ordinal features. And so I've partitioned it into 1, 2, 3, 4, 5 different regions. And the main idea now is anytime my test feature vector falls into region RL, or the Lth region, then I output a single number, ZL, which has been assigned to that region. And that can be visualized here. So this is Z on the vertical axis. So as you can see, like if I'm in region 1, then I always output this value, whatever the height of this is. So that's my Z. Z1 would be this height. If I'm in region 2, then I output this height down here. If I'm in region 3, I output this height here. And region 4 is this height, and region 5 is this height. Okay, so that's essentially all it is it's kind of like a lookup table. In a sense, you figure out based on the features which region you're in, and now that you know the region you're in, there's a table of output values per region, and you just output that. So the main question is, if you're going to train this model, how do you select the regions, and how do you select the output values assigned to the regions? In terms of some terminology, So this is a little bit more about how we might assign those outputs per region. So assuming that the regions are fixed, we have some way of doing that. Let's say if we're doing regression, you could look at, let's say you declare this subset SL as all the indices in your training data set whose features are in region L. So if I, let's say, extract all the indices I whose features are in region 1, and then I look at the labels, the corresponding labels, so the labels in that same region, I could just compute the sample mean and set ZL equal to that sample mean. So like the output here is just equal to the average of the targets for the features that fell into this region. 1 here is the average of the targets for the features that fell into that region, and so on. So that's what we could do for regression. Does that idea make sense? Okay. Now for classification, that's not going to work because let's say maybe I have binary classification, I have labels 0 and 1. I have to output a 0 or 1. I cannot output anything else. And so if I took the sample mean, maybe I would find that the sample mean is somewhere between 0 and 1. That won't work. So instead of using the sample mean, we could use the sample mode, which is the most common value in that target set. So I look at all the labels for the features in this region, and if I find, in a binary problem, if I find there's more 1s and 0s, then the mode would be 1, and I would set Z for that region at 1. So it's a simple extension. Instead of sample mean, you use sample mode. Same idea works. Okay, so there's still a couple questions. One of the main questions to ask, to figure out, is how we split things into these regions. Another question is, why are these things called decision trees? What about this is tree-like? Well, it turns out the connection to trees comes from the fact that when we construct these regions, we construct them in such a way that we threshold one feature at a time over multiple steps. So this will give us a decision tree. Okay, so essentially, the root of the tree is the full domain of our original features. And the leaves of the tree are these decision regions that we created. And the procedure to go from the root to the leaves is as follows. You start with your, let's say this is our full domain of our features. Then, what I'm going to do is I'm going to threshold one feature at a time. So I'm going to first say, is x1 less than or equal to this threshold t1? If it is, then I'm essentially creating one big region here as one case, and then if it's not equal to it, then I have this other region here. So I've done this big split of my data, partitioned it into two regions. Now I go further. Let's assume that it was less than t1. Now I can do another split, but now I'm going to split according to x2 and some new number t2. So if x2 is less than or equal to t2, then I'm in this region. On the other hand, if it wasn't, then I'm in this region. Now we can come back to the other case where originally x1 was greater than t1. So maybe I can do another split. x1 is less than or equal to t3. If that's the case, then I'm in this region. Otherwise, I can still do one other split. x2 less than or equal to t4. And that will mean that I'm in this region instead. And so in doing this, you can see how we can start with our original space, so we can chop it up into smaller and smaller spaces. And at some point, we have to decide to stop. And at that point, we have a number of different regions that we have arrived at by thresholding one feature at a time. So in other words, all these partitions will be vertical and horizontal lines, never a diagonal line. Okay. So this is why we call these things decision trees when we implement them this way. And it's a very simple, elegant, fast way of doing things. To do things this way. Of course, maybe if there was some way of looking at several features at a time, it would be more sophisticated, but it's not clear that that extra sophistication would be worth all the extra complexity that would entail. Turns out that even by doing things this way, we can get really state-of-the-art predictors. Okay, so any questions on the overall way that we split the data or why things are called trees? Okay, all right. So let's talk a little bit more about how we do the training. So they're trained in what's called a top-down manner, which is sort of a recursive procedure similar to what I described here for the classification or the prediction, but this is now going to be for the training. So we start with our original training data set, which has n samples, and let's define this index set that contains all the sample indices 1 through n. So that's what we start with. So now we're going to split this S into two subsets. We're going to partition it so that the labels are most homogeneous, meaning most similar, within each subset. So that's essentially the idea. So, okay, what do we have to choose? When we do this the first time, in this case of two features, there's essentially two decisions to make. I have to decide, first of all, which feature am I going to use for my split, either x1 or x2. And secondly, if I choose x1, I have to figure out what threshold to use for my split. So let's imagine that I have chosen my feature to be j, and I have chosen my threshold to be t. Then if we're talking about an ordinal feature, just as we did before, what I do is I declare, I do this comparison, xij less than or equal to t. But now I'm going to do this for all I in my data set, and I'm going to figure out which of the I in my data set actually gave me xij less than t, and I'm going to call that subset of indices S1. And now all the ones that are greater than t, I'm going to call that subset of indices S2. And so together, S1 union S2 is S. Okay, so this is a way we can split. Now for the categorical case, we don't have numbers, we have categories. So I can do a splitting, but the splitting won't be according to a real number threshold. It will just be one of a finite set of ways that I can split those categories. So maybe I have A, B, C, D, and one possible way of splitting that is A, C, in one subset, B, D, in another. But of course, there's different splits, but a finite number. So overall, we would like to find the best split every time we do this. I want to figure out what's the best variable to use first, what's the best threshold to use. So essentially to do this, we have to do some sort of joint search over the features and the thresholds. So in practice, we could do this just a brute force way. We could have a for loop over the different features. And for each feature, what we can do is we could sort so I'm looking now at feature J, I'm going to sort Xij. And now, in terms of splits, there's exactly n minus 1 different ways I can split it once I sort it. I either keep the smallest one, threshold right after the smallest, or second after the threshold after the second smallest, or the third smallest, or so on. So those are ways I could determine my thresholds. I could look at every one of those. So outer loop over features, inner loop over thresholds. And then I have to have some sort of metric for how homogeneous that is. How similar things are within, the labels are within subset 1 and subset 2. So we'll discuss some metrics for homogeneity in just a moment, but that's essentially how we do it. We would search jointly over features and thresholds, find the best split. Now that I've split into S1 and S2, I repeat. I take subset S1 and I do a further split of it. These are all in subset S1 here, and now I do a further split. And so I have to do this again for that subset. I again figure out which feature I want to use for splitting, which threshold I want to use, and then I evaluate the homogeneity at all the possibilities, and I do another split and so on. Eventually, I have to have a stopping rule. I have to decide when to stop. So one kind of obvious place to stop is when the labels are perfectly homogeneous within a subset. In other words, all the labels are the same. Then there's no reason to split further because, you've sort of, if you could get to that point in the tree, you would have perfect prediction, zero training error, essentially. Now there's other ways to have stopping conditions. You might instead say, I want that at the leaves of my tree, I have a minimum of 10 samples per leaf. I don't want to split any further than that. You could also say, I want a tree that has a depth of at most 3 or 2 or 1. There's all sorts of different ways you can come up with stopping rules. And so this is one other thing to decide in your overall approach. Okay. So I'll give you an example next, and then we can talk specifically about these homogeneity metrics for regression and classification. Yes?
So in the last line, it says that the decision boundary is always parallel to the coordinate axis. So I think decision tree may be very easy to get over fitting.
Yes.
So are there any special pruning techniques?
Yeah, so there's a whole world of decision trees, but as we'll see, what tends to work really well is to ensemble these trees. because they have individually very low bias, very high variance. And so if I can ensemble them, I can reduce that variance.
Okay, so there is no techniques for a single decision tree.
Oh no, like I said, there's a whole world of research on decision trees. But I would say in the contemporary world, people do not build individual decision trees and just have one tree. It's very easy to build a tree that perfectly classifies your training data. Just by making it powerful enough, you can perfectly classify your training data. Now, that's not going to generalize to test data. So what can we do? So what I'm saying is the most popular thing is to train many different random ones of these and then ensemble them. That is a very popular approach, still used a lot today. But single decision trees, I'm not aware of people actually using those. So.
Thank you.
Okay, any other questions? All right, so let's do an example. So here we have a data set that is like a car insurance problem. So we have these applicants, and essentially there's two features. There's the age of the applicant, the kind of car they're driving, which is categorical, and then the thing that we want to predict is their risk class. So are they a high-risk driver, low-risk driver? And so, the insurance company this is the training data that it has, but of course, in practice, when they apply this, they only get these, and they want to predict this label here. Okay, so the first thing we have to do is figure out which feature do we use. So let's investigate the age feature. Let's just sort things a little bit easier than is in the table. So we have 17 is the smallest, then we have a 20-year-old, 23-year-old, 32, 43, 68. And then let's put the class. So we have high, high, high. And then we have the 32-year-old is low, 43-year-old is high, and the 68-year-old is low. Okay, so that's one way of partitioning the data. We have another way of partitioning the data, which would be the car type. So we have okay, so if we have, let's just do it with family first, and then sports, and then truck. So for the family car type, you can see we have several samples. We have 3 samples, and they have high, low, high. And for the sports, we have high and high. And for the truck, we have low. Okay, and remember that our goal is when we do the split, we want to make the subsets as homogeneous as possible, as similar as possible. So if we split by age, we have, I could split here, I could split here, I could split here, and so on. If I split here, you can see this might be a good split because we have all the same labels on this side and almost all the same except for one on this side. If I split here, that's going to be worse, I think. This is 50-50, and this is not perfect. So we haven't really discussed concrete metrics for homogeneity yet, but just from an intuition, you can see that probably the best way to split this would be right here. Now, of course, we could also split the car type. We could split either here or we could split here. And splitting here is not that great. You get basically each side has 2/3, which is not as good as this split. Or we could split here, and I guess that would be another one. This would be perfect, and then we could further split it on there. Anyway, we're going to decide to first split according to age, and we're going to put it right here. And so to come up with a concrete number, we're just going to do the average of those two, 23 and 32, which is 27.5. So that will be the first partition in our data set. And as you can see, if the age is less than 27.5, we have all these high-risk drivers. There's no need to split that any further. Okay, now we're going to look at what remains, which are these. So these guys, we could split further along the age. Well, actually, no, there's no really nice way to split the age any further, because we could either split into those subsets, and then this is 50-50, or we could split into those, but this is 50-50. So what about when we look at the remaining drivers, we have maybe I'll write down those three. So there's the 32-year-old. So that person drives a truck. And then the 43-year-old drives a sports car, and the 60-year-old drives a family car. Okay, and basically, sports car, it's high. Family, actually, yeah, this. Yeah, low, right? Okay. So this is a categorical split. So we can either split into this one, split it that way, split it this way, or there's one other way we could split it, which is basically this way. So take the sports car driver out, and then have the rest as the other class. And if we do that, we get actually perfectly homogeneous samples in both classes. We get low, high there. So this is one way we can build a tree, where you can see with just essentially two decisions, we can get perfectly homogeneous samples. But this also motivates, like, how exactly, in general, do we come up with a metric for homogeneity for classification and regression? Clearly, we need that in order to actually do this with real data. Any questions on this example? Okay, so let's talk about regression first. So the goal is to maximize homogeneity or similarity within the subsets individually. Another way to do it is to say you want to minimize inhomogeneity, or minimize differences within those subsets. And that's, I guess, the way it's typically thought of, because often we're minimizing some cost, and so we're going to define our cost in terms of dissimilarity. So if we're doing regression, our labels are real numbers, then one thing we could look at is we could just look at the variance after we do the split. So we look at the variance in S1, and we look at the variance in S2. So how do we compute the variance? Well, we want to use the sample variance estimator, which looks something like this. This sample variance estimator, we're of course, so this is just for generic L is either 1 or 2. We first have to compute the sample mean of the data of the labels in that subset, and then once we have that sample mean, we can compute a sample variance. And now we're going to have two different variances, variance for this one, variance for this one. And in order to boil this down to one number, we can finally compute the average variance over these two sets. And because we have different numbers of samples in each set, we have to weight things this way. So at the end of the day, we get a number that depends on mu L, which depends on how we place that threshold. And so we just have to do, we have to look at the different features, we have to look at the different thresholds, and for every one of those hypothesized ways of doing the split, we can compute this variance, and we can find out the split that minimizes the variance. If we have outliers in our data, then instead of using variance, we might instead want to use absolute error, which is less sensitive to outliers. So we just, replace this, replace the above with this. And there's many other things you can do as well. We will see a more sophisticated metric when we discuss XGBoost on Wednesday. Or maybe Friday, we'll see. Okay, so this is for regression. Any questions? Okay, what about classification? So in classification, let's just set up some notation. So imagine that my class labels are in the set A1 through AK. And let's say for subset SL, we can make this empirical label probability mass function. So we're freezing L, but we're varying K through all the different possibilities here. And these are going to be now probabilities. So this is the probability of the data labeled A sub K in subset SL. And we can compute this using the simple average. So here's one of our indicator functions that turns on when yi equals AK, but otherwise is off. And so we're just summing how many times the training label is in the kth class for all the data in SL, and then we're dividing by the size of SL. So this is how we build this empirical label PDF. Once we have this, we can compute some more statistics. So one, probably the most popular measure of inhomogeneity in this case is called the Gini impurity. So this is the average Gini impurity, which you can see is just an average of the Gini impurities for the two subsets. And so for the Lth subset, the Gini impurity looks like this. It's 1 minus the sum of the squared PMF value. And so if you think about it, the kind of extremes that you can have in terms of being perfectly homogeneous. Okay, so obviously perfect homogeneity would mean that all the samples in that subset have the same label. And if you think about that, what does the PMF look like if all the samples have the same label? What does it look like? So the PMF is a vector. So what does that vector look like? Is it impulse? Exactly. So it's like one of the elements in that vector is 1 and all the other elements are 0. That means that all the data has that. And if it's the kth one that has turned on, then all the data is in the kth class. So that's one extreme. And if I plug that extreme into here, plug that impulse into here, I'm going to be squaring the impulse values, which one of them will stay 1, the others will stay 0. I'll sum them up. This is going to be 1. 1 minus 1 is 0. So this is the the least inhomogeneous. The most homogeneous is the least possible inhomogeneous. So that's one boundary. Now, what's the opposite? If I have a PMF and I say my data is just uniformly spread across all classes, what does the PMF look like in that case? Yeah, uniform. So every value is 1 over capital K. If I plug that into here, I square those, I get 1 over capital K squared, and then I sum over K, I get 1 over K. So the largest possible thing I can get here is 1 minus 1 over K. So otherwise, you'll always be in this range, and that will tell you concretely, according to this definition, how inhomogeneous your data is in that subset L. So this is just probably the most popular way of doing this. Although there are other ways. You can measure the entropy, you could measure misclassification error, something called chi-square. If you want to read about them more, you can read about them in this textbook. But it's just to kind of give you a flavor of what's done. Yes?
What does the magnitude of S1 divided by S refer to?
So whenever you have a set those bars mean the size of the set, the cardinality. Yeah. Right, so this is the size of the subset S1 over the size of the total set. So this is just like the proportion of the data in S1. Okay, so that's just, now you've seen a lot of the details about how you train these trees, about all this stuff. So let's step back and reflect on overall advantages and disadvantages of trees relative to some of the other methods we've seen before this quarter. So the first thing is we see these decision trees are very general. We made very few assumptions about our data. The features can be ordinal, categorical, mixed, no problem. The labels could be discrete, categorical, ordinal, that doesn't matter. It can work essentially with any data set. In fact, you do not even need to standardize your features. It doesn't have any effect on the tree at all. However, in practice, you should worry about imbalance labels. We've talked about this before back in Unit 5. That would be the case where, let's say, I have a classification data set and 99% of my training labels are in one class and 1% are in the other class. If I naively train a classifier to minimize accuracy, I'm going to get a classifier that just always predicts the majority class, and it's going to just ignore the minority class. So this is also going to be a problem here. So you have to, as always, balance your labels. We talked about different ways of doing that, like maybe you take the minority class and you just copy and paste those data samples until you have as many as the majority. There's various techniques you can use, but once you've done that, once you've balanced your data, you can just throw it at a tree, and it works quite well. Okay, another advantage, very different from other things we've seen, like neural networks, is it's very interpretable. It's called a white box model, opposite of a black box model like a neural network. In other words, like once you've trained a decision tree, and somebody asks you, like a lawyer says, explain your method because I think you wronged my client. And you say, well, okay, this is what it is. First look at the age, then look at the car type. It's very explainable. If you trained a neural network and the lawyer says, explain your neural network, it's like, you have no explanation for it, right? It's just something mysterious happened and it works, or I thought it worked, maybe it doesn't work. So that's a huge advantage to these trees. And there actually are a lot of applications. In reality, like maybe if you're using machine learning to do something in the insurance agency or something, you actually have to have an explanation for your model that you can provide to your legal team or to shareholders or whatever. And in a lot of cases, that means you can't use a neural network, but you can use something like a tree model. Another advantage is that these are actually quite fast in terms of the size of the data set. So you can say that they're on order log of n. And so let's think about why that is. So if I have a data set of n samples and I split it in half, in my first decision, now I have these half-sized. And in my second decision, I split those in half and so on. How many times can I split in half until I have just one sample left in my leaves, right? Basically log 2n. That's how many times I can split in half until I can't do any more splitting. Now in practice, maybe we won't split exactly in half. Maybe it will be 2/3, 1/3. And maybe we won't stop all the way when we have one sample. Maybe we'll stop before that. But as you can see, overall, it grows logarithmically with the size of our training data set, which is great because if you think back to support vector classifiers and support vector machines, those are actually order n squared, which is a big problem. As you may remember running some of the code in the labs, it takes forever to train those SVMs and even to use them for prediction. Even that takes forever. So these are very fast in terms of the size of the data set. Now, okay, what are the disadvantages? Well, when you train them, the training procedure can be expensive if you exhaustively look at all your features every time you do a split. So one solution to that is don't look at all your features every time you do a split. just restrict to a few randomly chosen features at each split. And because you don't have many features to check, this massively reduces the complexity of training. And this also works well if you're going to ensemble this, and then we already talked about using randomly chosen features just for the sake of ensembling and getting diverse predictors. Another thing which we talked about briefly before was these methods are prone to overfitting. So it's very easy if you give me a deep enough tree that I can perfectly classify the data, my training data. In fact, as long as I just go until I can't do any more splitting, I can perfectly predict all my training data, right? But that doesn't mean it's going to generalize to a test set. So we could say that these trees have very low bias, very high variance. Another way to understand the variance is that if I change one sample in my training data set, that actually might ripple through and change my entire tree. So, right, very sensitive to details in the training. So how do we regularize these things? How do we make them less prone to overfitting? For example, you could use a minimum number of samples per subset. You could force the tree to stop at some maximum depth. All those things are going to make your tree more biased, but have less variance. There's a really good overview of these decision trees in the sklearn documentation if you'd like to learn a bit more. Okay, and the very last thing I want to say to finish out today's lecture is now that we have seen all the ingredients, so we know that we have decision trees, a very convenient method, but their main issue is that they tend to overfit, very low bias and high variance. But we also learned about these ensemble methods, which are ways to combine models. And so essentially what you can do is you can generate an ensemble of trees where for each tree you use a random subset of data and a random subset of features at each split. And then you can average them together. And so here's just one visualization. This is on a two-dimensional data set. This is the 2 moons data set. You can see there's red and blue samples roughly like that. But, quite noisy, not something that you could do a great job of linearly separating. Anyway, I can train different trees, and you can see all my trees are a bit different because I used maybe a different subset of data, maybe different random features at every split. And the trees individually don't necessarily do a great job, and they look a little bit weird, as you can see, too. There's like these strange decision regions here and so on. But when you put all these trees together, you get this, which actually looks like a pretty reasonable way of splitting this data set. Okay. And in practice, if you look at the documentation for the random forest classifier and regressor, you can see that the defaults are often to use what are called decision stumps, which are a tree with just one split. So super simple to train, and then you use many of them, like maybe hundreds of them. And you put them all together, and the bias goes down because you average them, and the variance, I guess because you're averaging them, they're all biased in a weird way, but on average their bias goes down, and then the variance also goes down. And overall you can get really, really good performance. Maybe some of you guys have tried these already for the project, but a random forest usually just out of the box without any adjustment gives you quite a good model. And now that you also see, all the different ways that you configure random forest, you can try different things in terms of hyperparameter tuning. You could try how many different trees you want to use on the average, what are the depths of the trees, and it has all the different parameters. You can configure all these things we talked about, and you could try to tune them and try to do better than the out-of-the-box default performance. All right, so that's all I had for today. Are there any questions about anything? Okay, great. So next time, we'll talk about a different method where instead of training things in parallel like we did, we're going to train them sequentially. So we're going to have one model that we train, and then we're going to have another model that fixes the errors the first, and then another model that fixes the errors in the second, and so on. And this is just another way, and then finally we'll average all these models. So today we talked about the parallel method. Next time we'll talk about the serial or sequential method. All right. See you guys on Wednesday.